Well, hello and welcome to this webinar. My name is Simon Ritter. I'm the Deputy CTO at Azul. As the title says, we're going to be talking about what's new in JDK 21. JDK 21 was released a couple of weeks ago, and we'll be talking about all the new features that have been added. It's quite an interesting release in terms of having quite a lot of things in it. Before we get going, there's a couple of things that we need to talk about in terms of housekeeping. We will be recording this session, and we will make a copy of the recording available to you afterwards so that you can share it with your colleagues, your friends, or your family if you want to. And we'll also be having questions and answers at the end. If you do have questions as we go through, then please feel free to type those into the Q&A box on the Zoom interface, and we'll deal with those at the end. Right, so let's get going on what are the actual new features. Well, the first thing is not really a feature. It is a feature, but not a functional feature, is the fact that JDK 21 is a long-term support release. Now, this was something that Oracle introduced as an idea for their builds of the JDK from JDK 11. And this was when they changed to having a twice yearly, 6-monthly release cadence for the JDK itself. When they did that, they decided they'd make JDK 8 a long-term support release, even though it had already been released some time ago, but they said that they would continue to provide updates and maintenance for that. The next one was JDK 11, and then they said there would be 3 years between long-term support releases, hence JDK 17 being the one after that. At the point where they released JDK 17, they changed their minds again, and they said it would only be 2 years between long-term support releases, which is why JDK 21, 4 releases after JDK 17, is now a long-term support release. The good news is that even though Oracle introduced this as an idea for the Oracle JDK, all the other Open JDK distributions have followed that. And so people like Azul, with our Zulu builds of Open JDK and our Prime JVM as well, follow the same cadence. So we're providing JDK 21 as a long-term support release. So we'll have 8 years of updates followed by 2 years of passive support as well. So I think that covers all the kind of major details there. In terms of licensing around the Oracle JDKs, we'll mention one more thing, which is that this 2-year release cadence also affects the license that's used for JDK 17. So JDK 17 is currently under what's called the Oracle no-fee terms and conditions, and that allows you to use the Oracle JDK in more places than you would have done previously without having to buy a Java SE subscription. Essentially, it says that for any internal business use, then you can use the Oracle JDK without a Java SE subscription. Now, the reason this is significant is because the way that they do that license is that the no-fee terms and conditions license only continues until 1 year after the release of the next long-term support release, which is JDK 21. So it means that you've got less than a year now. If you're using JDK 17 from Oracle, less than a year, the license will change and it will revert back to the Oracle Technology Network License Agreement. And that is more restrictive in terms of where you can use it without a Java SE subscription. So it does mean that if you're using Oracle JDK 17 at the moment, you need to think about what you're going to do next September when JDK 23 comes out, because that will then result in a licensing change. Okay, let's move on to what the actual features in the JDK itself are. Well, as I said, this is quite a substantial release in terms of the number of changes. And changes, as I'm sure many people are already aware, are defined through what are called JDK enhancement proposals, JEPs. And in terms of JDK 21, there are 15 JEPs included in that. So like I say, it's quite a big release. And some of these are quite chunky as well. What I've done here is I put what I call the primary JEPs. We'll talk about the smaller ones right at the end, just to kind of cover out everything that is included in JDK 21. But these are the primary JEPs. Now, I won't actually talk about these on this slide because I'm going to talk about all of them as we go through the rest of the presentation. So there isn't really much point in covering them at this point. But as you can see, lots of interesting new features going on here. Right, first one, let's talk about threading in Java. Now, threads have been in Java right from the very beginning. It was one of the things that made Java a really popular programming language, was unlike languages like C and C++, where you needed extra libraries and it was quite complicated to do multi-threading in those languages. Java had multi-threading built in right from the very beginning. And we've seen a lot of changes over time in terms of making that easier and easier. When JDK 1.0 came out, you had the thread class, and coordinating threads was quite difficult because you literally had things like sleep, wait, notify, and interrupt to do that. And then we saw with JDK 5, the introduction of the concurrency utilities, things like semaphores, mutexes, read-write locks, and so on, higher level primitives to make it easier to do that concurrent processing and have coordination between different threads. And then in JDK 7, we got the fork join framework, which allowed us to have a task which we could decompose recursively until we got to a small enough level of granularity, and then we could have that processed by a number of threads. Again, making it easier to do that kind of task. JDK 8 introduced the idea of streams, so we could do parallel tasks without having to see the code itself and just create a stream of objects and do it that way. What we've got in JDK 11 is an approach in terms of how threading works at a lower level. So what I've done here is I put a diagram which shows how Java threads map to the operating system threads underneath. And we can see here that there's a mapping in terms of a Java thread to an operating system thread, a one-to-one. Each Java thread you have in your application matches to or maps to a single operating system thread underneath. And then the operating system is responsible for handling when those get scheduled onto specific cores or CPUs through what's called a preemptive scheduler. What this allows us to do is to run things in parallel, because even if you don't have as many cores or CPUs as you do Java threads, the scheduler will make sure that by doing time sharing between those, you can have the illusion at least of things happening in parallel, even though they're not technically happening in parallel. You get the illusion of that through the time sharing way of doing things. Now, that's all very good. So it's worked very well up until now. But the problem is that if you look at using lots and lots of Java threads in an application, it really doesn't scale up to very big internet workloads. What that means is that if you want to use tens of thousands, hundreds of thousands, even like a million threads, you're limited in terms of the amount of resources it just takes to do that. If you look at a basic thread, what you're looking at is a minimum of 2 megabytes of virtual memory in order to create that thread. And that's just to create the stack, the necessary structures for that thread. If you want to run a million threads, that means you're going to need 2 terabytes of virtual memory to do that. Now, that's going to be a lot of memory to run that kind of application. So one of the other things that we see when we scale up to these very, very large numbers of threads is that they're using a specific threading model, programming model, that results in this very large number of threads. This is called thread per request. You're running something like an application server, a web server, and each request that comes from a client running on a web browser, let's say, or another microservice, for example, each time they send a request, you create a new thread to handle that request. And to make life easier, often people will pool threads to try and handle the workload across that. But the idea is you have one thread per request that comes in. This is good because it isolates the workload from other requests. So you're having a nice self-contained request, everything can be handled by a single thread, and off you go. Problem with that is that most of those threads need to interact with other resources. It could be reading things from a database, it could be accessing a file, it could be calling across a network connection to, say, another microservice. As a result, those threads are going to spend most of their time actually doing nothing. They're blocked on I/O, and they're just waiting for that I/O to complete. That means that those threads are sitting there not doing anything. Now, again, like I said, people have come up with solutions to this in terms of doing thread pooling and trying to interleave work with those threads so that when a thread does block on I/O, you've got things like reactive programming, that type of approach, RxJava. All of these are trying to solve that problem of when a thread blocks, can we reuse it for doing work whilst it's just sitting there doing nothing? So the idea behind virtual threads, which have been included in JDK 21, they're introduced as a preview feature back in JDK 19. They're a full feature now in JDK 21. And what this allows us to do is to share a platform thread amongst a number of virtual threads. Here I've shown a diagram to make it easy to understand what I'm talking about here. So the thread that we had before, where we mapped each Java thread to an operating system thread, we still have that concept of a Java level thread that maps to an operating system thread one-to-one. But what we're now calling them, rather than just a thread, is a platform thread. A platform thread is then able to be shared by multiple virtual threads. As a programmer, you can use either. You can use a platform thread if you want to, or you can use a virtual thread. If you use the virtual threads, then those get shared between a single platform thread. Now, in terms of, as I said, the way that you can use this in your code is you can use either of them. So you can use platform threads, which is the old side of doing things, or you can use virtual threads, which is the new way of doing things. The great thing about this is that you don't have to think about virtual threads really being different from a program point of view to platform threads. You're still using the thread class. So all of the methods that you have in terms of the thread class apply to both platform threads and virtual threads. The real change that you need to think about there is primarily how you create your thread. So the thread is created using a slightly different way of doing things. I'll show you an example of that in a moment. But other than that, there are the major changes that you need to consider are more about the structure of your program rather than how you interact with that thread. There are some very important details to be aware of when it comes to virtual threads. So the first thing is they are not a magic bullet. Using virtual threads will not guarantee better scalability or better application performance for your application. So don't think to yourself, oh, right, we've got virtual threads. Let's change all of our code to use those virtual threads in the application because we're going to get better scalability and we're going to get better performance. Don't think of it like that. You need to think very carefully about how you're using those threads in the application. So the one thing is, like I said, that the kind of task which is really suited to them is ones where you've got a lot of I/O going on, where you're blocking, waiting for a database connection to complete, waiting for a file read to complete, and so on. If you're doing CPU-intensive application code and spending a lot of time using the CPU, that's not going to help you because all that's going to happen is that virtual thread will continue to do the work that you're doing on the CPU, and it won't be able to have the platform thread underneath released and then used by another application thread. There are a few other things to be aware of with virtual threads. Now, I mentioned with the first diagram that you have a preemptive scheduler that's used by the operating system to allocate a certain amount of time to each thread so that they are shared fairly, at least fairly by process priority or thread priority. They're shared fairly between the available resources. Now, that doesn't happen with virtual threads. Virtual threads don't have preemptive scheduling. They're scheduled based purely on when the JVM realizes that there is a time when that thread can be used. So when it blocks on I/O, then the JVM will see that and it will say, right, that thread that's currently waiting on I/O will pull the platform thread from underneath, change that, use a different virtual thread and allow that to run. But if you don't release it through I/O, then it's not going to get preempted by the JVM. It will not do anything that's in terms of fairness of sharing that. What this also means is that you need to think carefully about how your code works. And this really is a longer discussion, which we don't have time for in this particular webinar. But how you use synchronization is quite important because if you have synchronized blocks, synchronized methods that you use, which hold a lock on an object, then that will pin a virtual thread to a platform thread. So even though it might be doing I/O in that synchronized block, it will still be pinned and it will still not be released so that you can do other work elsewhere. So it's very important to look at how you're using synchronization when you switch to using virtual threads. The other thing that's very important to know about this is don't use thread pooling because you're effectively kind of defeating the idea of what's happening underneath with the JDK and the JVM. So those are kind of things that we need to think about. Like I said, we'll do another webinar about this at another time where we'll talk more about what's happening with virtual threads and go into more detail about that. Okay, the second thing to understand about virtual threads is that there's a couple of other JEPs that have been included in JDK 21 which relate to that and help in terms of how we can make concurrency easier to do. So the first thing is what I put here is an example of unstructured concurrency. And what's happening here is that we're handling a request. And so we've got a method called handle. And what that needs to do is it needs to spawn off two separate threads to do some work, which will call other things and do it in parallel. As you can see here, we're using the future, and so we're submitting to a thread. We're using the code here. We've got a Lambda expression where we're saying, okay, we want to find a user and we want to fetch an order. So we can do that in parallel concurrently. We create the futures, and those two methods will get called. But what happens then is we need to wait, obviously, for those both to come back and complete. We do that by calling the get method on the different methods. So the find user, we got the get method on the user object, that's the future object that's returned. And we've also got the future for the order. We call the get method on that, and that will return when the result is available. But this is not ideal, because what we're then going to do is we're going to return a response, which is both the user and the order. Great. The problem with that is what happens if one of those things doesn't complete in the way we expect it to. So if we call the find user, and maybe that throws an exception. If that throws an exception, but we're still doing the fetch order, there's no way to cancel the work that's being done by the fetch order, even though we've thrown an exception from the find user. So we're not going to be able to do the result, but we have to wait for that. So it's kind of like a dangling thread that we get there. The other thing is that if let's say the fetch order takes a long time to complete, we're waiting there for a long time whilst we've got work going on, and things that are not being responded to, and things like that. So this is unstructured concurrency. We've got two different things happening at the same time, potentially more, and it's not ideal in terms of how we can deal with situations where we've got very similar time taken to get the results. So each subtask can succeed or fail independently, and that has an impact on what we do. And what happens if the find user throws an exception, handle method gets interrupted? What if find user takes a long time to complete, fetch order completes quickly, as I've said? What we get in JDK 21 is the idea of structured concurrency. And this has been introduced as a preview feature, so there's still time for it to be changed before it makes it into the final version. What we can see here is we've got our handle method, but now we're effectively doing the same thing in that we are starting off two subtasks, but we're doing it within a structured task scope. So this is the structured concurrency. A new library introduces a structured task scope. Now that implements the closable interface, so we can put it inside a try with resources block. That's very good, because that means that we then guarantee that things get tidied up when we exit the block. So in this case, we're creating a new structured task scope, and we're using shutdown on failure. There are different ways that you can start that structured task scope, but in this example, we're saying shut down on failure. If one of our subtasks fails, we shut down all of the other tasks. We don't have to continue waiting for, let's say, the fetch order to complete, even though there's nothing that we can do with it when we get it back. So in this case, we create now, rather than using the future, we create a supplier, and we use the scope of our structured task scope reference, and we fork off a separate thread, use our Lambda expression to indicate what we want to do in that thread, which is find user or fetch order. Then what we do is we say scope.join, and we join those subtasks, and we throw if failed. So we can propagate the error through the stack if we need to. This is really good because, like I said, if one of those tasks fails, then we will shut down the whole set of tasks immediately, and so we can return having thrown an exception, and then that means we're not waiting for things to happen. So this is much better in terms of allowing us to have error handling with short circuiting. We can see that if one part of the task throws an exception, then we don't have to go through everything else. We can do cancellation propagation through that. It's much more clear, so we have better clarity on that, and we have observability that's better. And what I mean by observability is that the stack traces that are generated through the structured concurrency API mean that it's much easier to see where the error occurred, rather than having to look through the different stacks that you get in the previous example. So this is a much better way of doing things. So structured concurrency, really good API. Scoped values is also something that has been added, which relates to the idea of virtual threads and the whole concurrency side of things. At the moment, we have thread local variables, and this is where if you want to have a local variable, which is for a thread, hence the name, But the idea there is you have a thread, a variable which is used by a particular thread, and its value can be changed whilst the thread is doing its work. So that's why it's a variable. That's useful because we want to have situations where we want to allocate a value to a thread, but maybe it changes as the thread does its work. And when we create multiple threads, we can assign different thread local variables to those, so they're isolated from the different threads. But we can obviously allocate different values to that when we initialize it to the each thread. So we use those when we're creating multiple thread applications. That's all good. But again, there are some drawbacks with this. They are valuables, they are values, therefore they are immutable. Sorry, scoped values are values, so they're immutable versus variables. This is important because often you want to say, right, I want to give that value to the thread, but I don't want it to be changed. It's just going to be used whilst the thread does its work. This is good also from the point of view of performance, because with thread local variables, when you create child threads from that, you have to create a new copy of the thread local variable for each child thread. So it increases the number of resources you need and the amount of work that's required. Because we're using scoped values, which don't change, they're immutable, when you pass them to a child thread, you don't need to make a copy because it's a single value. And so there is no changing it. And so it can be shared between the thread and the child threads. So this is good in terms of that. If you want to use something like this, you can see the example code here. What we've done is we've created a scoped value, and we'll say that the context is from a new instance. And then what we're going to do is we're going to use our request again. So we'll serve a request, and we'll say that the context here, we're creating a context which is the request itself. So that's where the thread, the scoped value is going to be used. And then we use scoped value where with the context, and then we run where the thread is, where the scoped value is going to be used. So we run, and we provide the Lambda expression which shows what we're going to run in there. So we handle the request, and that's the thread which is going to have this particular scoped value assigned to it, and any child threads, as I said, would also inherit that as well. Pattern matching was another big thing that we've seen change over the last few releases of Java, and several things in JDK 21 are the finalization of these features. So pattern matching for instance of and records. We can do pattern matching on a record, and we could do that. Let's say we've got a point $x$y as a record. We could do that with using pattern matching for instance of, which is already part of Java prior to JDK 21. If I wanted to do that in a simple form, I can take a method called Pythagoras, pass in an object, check to see if it is a point using pattern matching, and then have a pattern variable p, which is the record. What I could then do is I can extract the x and y values from that point by assigning them to $x and $y, and then I can calculate the hypotenuse. But we can do better than that, and that's where record patterns come in. So record patterns are what are called a deconstruction pattern. And it's important to know that deconstruction patterns in this case only work with records. You can't use it with normal objects. But if you have a record, then what you can now do is this, where you can say if O instance of, and then you give the record definition. So you say point $x and $y. In that case, when you want to use that, you can reference X and Y directly. You don't have to do the extraction yourself. So you don't have to call p.x, p.y. You can simply reference X and Y from the record definition. And so you can see here we've done the square root of x squared plus y squared. It simplifies the code a little bit, eliminates some boilerplate code. So this is all very nice. The whole idea of record patterns is really, and pattern in general, is really good for Java. Now, the other thing about record patterns is they're composable. So let's look at what that means. If we take some example code again, and let's create an interface called rectangle, we'll reuse our record that we had on the previous slide, so $x$y. We'll introduce enumeration for color, red, green, and blue, and then we'll create a couple of records which also have records in them as the elements. Color point, which takes a point and a color, and then a color rectangle, which takes two color points to represent the top left and the bottom right. And we'll also say that implements rectangle just to make my example code easier. So if we use that, what we can do is we could say print top left X, and we pass in a rectangle. So it's some kind of rectangle, implements the rectangle interface. And then we can say if our instance of color rectangle, and we know that we can use the deconstruction pattern for record patterns there, and we can say color point top left, color point bottom right. And if we want to print out the top left X value, then obviously we'd have to do print line top left dot, call the P method to retrieve the point from there, and then call the X method on that to retrieve the X value. But of course, we know that color point is a record as well, so we can use deconstruction on that. And we could say print top left X with a rectangle. Now we do if our instance of color rectangle, color point, and give the record definition of color point, point P, color C, and then color point bottom right, which I've shortened to BR there. And now we only have to call one method, so we call P.X. But of course, we know that P is another record as well, so we can decompose that, and we can have if our instance of color rectangle, color point, point double X double Y, color C, color point BR. Then we can reference X directly. Now, obviously, when you start looking at that, you think to yourself, okay, that's good, but we're starting to lose some of the benefits of pattern matching because the code is getting quite complicated just to reference a variable X without having to call all these different methods. So we can simplify that a little bit by using the local variable type inference that was introduced in JDK 10. Here we can avoid a lot of that extra kind of typeness that we've got by using var. The compiler can figure out for us, as long as it's obvious to the compiler, then we can have point var x, var y. It can infer the types for us. Same for var c, var br. All of that can be inferred from what's in the rest of the code. But another thing that's been introduced in JDK 21 is a really useful new feature, unnamed patterns and variables. What this allows us to do is to say, okay, so we've got this color rectangle, color point, var x, var y, var c, var br. Great, okay, but the thing is, we're actually not interested in most of those variables. In our code, we only want to use X. So although we know that we have to say that there is a variable Y there, there's a variable C there, and a variable BR there, the compiler has to see those to understand that that's the structure of the records that we're using, and therefore it can do the correct type resolution and infer the right types that are being used. But we don't actually care about it. So what you can do now is take advantage of one of the changes that came in JDK 9, which was to make a single underscore no longer valid as a variable. So it's a reserved word. And what you can do is you can simply say color rectangle, color point, point, and then you say var x, because that's the one thing that we do actually want to use. And then for all the other parts of the record declarations, we can use a single underscore to say, yes, there is something there, but we don't care what it is. We don't even care what the type is or anything like that. So we don't even need to use var. We just go underscore, 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 and the compiler then knows that in terms of the record declaration, that there are parameters there, but we don't care what they are, so it doesn't need to do any extra work. So this is really good. This is kind of tidies up that part of the pattern matching when we're using records. Pattern matching for switch is another thing which has been around for a couple of releases as a preview feature and is now a final part of JDK 21. In the past, we've been limited in terms of what we can switch on with a switch statement or a switch expression. We could switch on integral values, we could switch on strings, we could switch on enumerations. What we now do is expand that to allow type patterns to be matched as well. And we can do something like this. So we can say type tester object O, then we switch on O, and we can say case null. This is a really good thing because they've now allowed you to have a case for null in a switch. That wasn't possible before. What it meant was we often had to put a test outside of the switch, which is essentially a multiple if then else. We had to have a separate if to see, is it null, do something with it. Now we can actually put a case in the switch to say case null, okay, null type, and then we can have patterns for the types that we want to look at. String S, so the type variable is S. We can reference that on the right-hand side of the arrow operator and print out the string. We have a color, we have a type variable, a pattern variable called C. We can call get RGB because it's a color object reference, and we can't do references to primitive types. So we can't do an int on its own or a short or a byte on its own, but we can have arrays of primitives because they are technically objects in Java. So we could do int array and have a pattern variable IA, and then we can print out the length on the right-hand side. So this is all good. So this allows us to do various things. Now, null, as I said, is good, but it's a little bit special. There's a couple of things to bear in mind about this. What they've said is that now all all switches must have a null case in them. And you can either do it explicitly or implicitly. Explicitly is in my code, you do a case null and you catch it. But if you don't do that, to maintain backwards compatibility, the compiler will insert one for you. So if I look at the code that we had before, and we say we've got case string, case color, case and case int array, what the compiler is going to do there is actually say, well, you haven't got a null in there, so we'll insert one for you. We'll do the first thing, and we'll say if it's a null, we'll throw a new null pointer exception. That means you've got compatibility with the way that the code would have worked before, so you don't have to worry about changing anything. You don't have to go back and change all your switch statements to include a null, unless you really want to. The other thing you can do, which is nice, is you can do a catch or a case on null and default at the same time. And that's really good because it allows you to say, well, if I've got anything that isn't in my list of things above and a null, then I want to do one single thing for it. So you have to have separate cases for it. Again, nice little tidying up feature that eliminates some problems that would have occurred if we didn't do that. Yeah, so this is what you could do before, but you can't do this anymore. They actually changed it in JDK 21. So you can't do case default. Pattern matching for switch completeness. This is another thing that's important to understand about this. If we do something like this, so we pass in an object and we have a switch where we're using the pattern matching and we only provide two different cases, string S and integer I, then what we'll see here is, yeah, obviously we can do that. But the problem is, what happens if we pass in something like a color or a float or any other kind of object? Now, you could argue that in this case, we should just ignore it because we haven't specified a case for it. But that's not the way this is going to work. They decided that to try and eliminate potential errors, what they would do is they would say, let's make sure that everything is exhaustive or complete so that you handle all possible types that can exist for that switch when you're using pattern matching. Easy way to do that is simply to add a default, because in the case of where we've got string and integer, to address all other possible types would be an infinite list of types. So we do that through default. And so now we are complete because we handle every single possibility. Now, the other thing that we could have done is if we have a sealed class. So this was, I say using previous example, and I didn't include that in this particular presentation. But if we had a sealed class where we had a shape as a superclass and then triangle, square, and pentagon as subclasses of that, then we don't need a default for that because it's a sealed class, then we can handle all possibilities just by saying case triangle, case square, case pentagon, and case shape. And that means that we have got a complete switch statement and we don't need to worry about adding a default there. The other thing that happened in JDK 21 was that they changed the way that what are called guarded patterns work. Guarded patterns means that you have a case where you've got a pattern for a type, so triangle T, but you also want to add another test to that. And you can see here, case triangle T when T.area is greater than 25. It's a very logical kind of thing to want to do. You're checking you've got a triangle and you want to make sure if that triangle is bigger than 25. Now, in the previous versions, what they did was they changed that, or they had the idea of using the double ampersand, so the and operator, which is very logical because it was like case triangle T and T.area greater than 25. They then decided that they would change this to when, which is, I'm not sure that was the best idea, but they decided to do it. The OpenJDK developers decided to do that. So they've changed it to when. Now this has some implications. Where when is important. So I put together some examples of how you can use this in ways that you shouldn't do. Let's say we have a class, an abstract class called interrogator, and it's a sealed class that permits who, what, when, where, when, why. And then we've got a final class when, which extends interrogator and has a method called when in it. Okay. What that allows us to do is to use our switch with pattern matching for types, and we can say something like this. We can do pass in an interrogator, we can do switch on question, and then we've got cases here for what, we've got a case for where, we've got a case for why, and we can return out what, where, why, and we'll even add in a default, even though it's a sealed class, to say how. Let's also assume that we have two more methods called where and why that are local. What we can now do is we can add in a case which says case who, what, when, where, why. And the reason we can do that is because we're pattern matching on the type who, and then we're going to use the pattern variable what. We're going to use when to indicate we've got a guarded pattern, and then we're going to use where to test to see whether it's true or false. If it is, then we're going to call why. So that still works quite logically. But we can go one step further than that, and we can be really silly, and we can have case when. The reason we can do this is because when is a contextual keyword. It only works as when it's in the right place. So here what we're doing is we're saying the pattern that we're matching on the type is when, but we're also assigning the pattern variable to be when. And we can do that because the compiler can figure that out, and the next when on its own, the second when on its own, is the guarded pattern, and then the test for that guarded pattern is using the reference to the pattern variable when and calling the when method on that. And then if we get a result that's true, then we're going to call the local when method afterwards. So the compiler can actually figure all this out, and it works, but I don't recommend it. String templates is another thing that has been added to the JDK 21. This is quite a nice thing because strings in Java are a fundamental part of the language, and we use them all the time. In JDK 13, we introduced string templates. That made it easier to do things like multi-line statements or multi-line strings. That was really good. But if you want to construct things where you're inserting values, that's always been a bit difficult. And there are different ways of doing it in Java. None of them are ideal. They've all got their advantages and disadvantages. So you've got simple string concatenation. You could use string builder. You can use string format. You can use string formatted. And there's even java.text.message format. So there's all these different ways of doing it. But they had their disadvantages. What they came up with was the idea of string templates. What that allows you to do is use a template processor, and that is called str. So that's your string template processor. It is automatically imported for you by the compiler. So it's a public static final. It's available to you whenever you want to use it. And you can do things like this. So here's a simple example. You've got two strings, first name and last name, Simon Ritter. And then you can use the template processor, str, and then you specify the string template that you want to construct. Here what we're doing is we're saying put in the first name space followed by last name, and that will obviously construct a string with my first name and my last name. If you wanted to do the same thing but reverse them so that you're creating a sort name to sort on the last name, then you can simply specify last name, comma, space, first name, and that way you'll get my last name, comma, space, followed by first name. Now, if that was all string templates did on its own, that wouldn't really be that much fun. But you can do more exciting things, more flexible things. Better than just string insertion. What you can also do is perform arithmetic. Let's say we have two integer values, x and y, 10 and 20. Now you can use the string template processor to say print out x and y, and then the result of x plus y. And you can do that calculation inside your string. You don't have to do it outside and have a separate variable for that. So you can simply put it into the string template processor, and it will do the work for you. And you can take that to the next level, which is you can say, let's call a method within the string template and have the results of that inserted into the string. Here, what we're doing is we're using the date time formatter. There was a slight change to that in, I think, JDK 19, maybe, where they added a B parameter that you could use that. So what we'll do now is we can say we are here and then put into the string template processor date time formatter dot of pattern B dot format local time now. And then what that will do is we'll call the method and say we are here in the afternoon learning Java. Great. So it inserts the result of that method. What's also really nice to see is that you can include new lines to aid readability, so long as they're inside the braces that you're using for the definition of what the template is. And you can even include comments within there. So that's nice as well. So you don't have to worry about any of that being kind of confused. You can put comments in there. You can use new lines to separate things out and make it more readable. Sequence collections. This is quite a small change, and it's funny because I was talking to Stuart Marks at Devox yesterday, and he was saying that it took him quite a long time to actually create this feature, even though the results are actually really quite small. But it's something that did take quite a lot of work and was necessary to go through all the details of it. We have sequenced collections in Java. So we have like a list, we have a deck, we have a sorted set. They exist. They have existed since JDK 1.2 when collections were introduced. This is all good. The problem is that there's no common interface or common superclass across all of those that indicates that these all have sequence. So, for example, list and deck implement collection, but sorted set doesn't. So, or so it does, but sorted set inherits from set, but doesn't have an order definition. So there's no common supertype until now. What that allows us to do is introduce sequence collections of type E, and that takes several new methods. So one new method, which is reversed, and then they took some of the methods from deck and kind of promoted them. So now these are available across all sequence collections. So you've got add first, add last, get last, remove first, remove last. Like I said, not a huge change, but a useful thing if you're looking at using collections and using ordered sequence collections. Unnamed classes and instance methods. This is one of those features which I know the developers of Java are trying to make it easier for people to get started with Java. We've seen things like JShell. We've seen things like the ability to run a Java source file, a single source file, without having to go through the compilation process. You can just simply execute a single shell file, a single Java file, without having to do the compilation. Great. What this does is to simplify some of the ceremony associated with your first Java program. So this is what we typically do, isn't it? We want to do hello world, and what we're doing here is we're saying public class, my first class, and then within that you've got to have public static void main, takes an array of strings as args, and then you do system.out.println hello world. There's a lot of stuff going on there. I've colored different parts of it to indicate all the things there. So you've got accessor modification through public. You've got the fact that you have a class, so you've got encapsulation, object-oriented, that you need to understand. You've got static references. You've got void as return type. You've got system.out.println to print something, so you've got to get references to that. Lots of stuff going on. And if you just want to print out hello world, that's a lot of things to understand from the very beginning. So what they've said is, let's try and make that easier. So now they're introducing the idea of instance main methods. So that means that we can have class hello world, and now rather than having public static, you just do void main and then print out hello world. And then to simplify that even further, let's forget about the class idea, and we'll add unnamed classes so that you don't need to specify a class name for it. So it's unnamed. And you just simply add void main, system.out.println hello world. If they can just get rid of the system.out reference, which I guess you can, but it'd be nice if they could find a way of simplifying that, then we're pretty close to having very, very simple hello world programs. Once you get beyond that, you do have to understand all the details of it. So it's good for the very beginning, but we do still need all the other stuff as well. Right, just to kind of wrap up other JEPs that were included in JDK 21. So I wanted to just run through these. I'm not going to go through them in detail because there's a lot of stuff here which is still not part of the core infrastructure. First thing is foreign function and memory API. That's a third preview. That's a replacement for JNI. That's been around for a while, obviously third preview. I just saw today that JDK 22 looks like that's going to be a final in JDK 22. So have a look at that. There's also the vector API, 6th incubator for that. So that's been around for a long time. That's programmatic control of single instruction, multiple data, vector instructions. When you want to use vector instructions at the microprocessor level, compilers sometimes can't determine how to use that. So what the vector API does is introduce a programmatic way of you specifying exactly how you want to use those vector operations, and then the compiler knows what it needs to do in terms of compiling them. Deprecate the Windows 32-bit x86 port for removal. So it's not gone yet, but it will be going pretty soon, hopefully. I'm sure there are not many people out there still using Windows 32-bit versions. Prepare to disallow the dynamic loading of agents by default. It could be a little bit contentious, but you need to understand this is only for dynamic loading of agents. So on a running JVM, you're still going to be able to do loading of agents at startup time through the command line flags. That won't be affected. That'll still happen quite happily. But this is where they want to try and restrict what you can do to a running JVM. This is around looking at security type things. So that is allowing that at some point in the future. It hasn't happened yet. Key encapsulation mechanism API. This is a fairly sort of deep, if you like, security type change. This is about key encapsulation mechanisms, chems as they're called, and these tend to be things that are used by higher level protocols like TLS. So it's just a way of having an API that allows you to access those kind of things. And then the last thing is generational ZGC. That's a low latency garbage collector that was included a while back, and they finally switched from using a single generation to using multiple or 2 generations for that. Just briefly mention Zulu builds of OpenJDK. That's what we do. So JDK 21 is available for free. We've also got 8, 11, and 17 as long-term support versions if you want them. Actually, we've got loads of other versions if you want them. But these are fully TCK tested. Commercial support is available if you want that through Azure Platform Core. Comes with time-defined SLAs for updates. We provide CPU and PSU versions for the platform core versions, and we also have JDK 6 and JDK 7 support available on there as well. Just to summarize then, JDK 21 is the new long-term support release, as I said. Virtual threads, very appealing for a number of things in terms of developers, DevOps, should improve some applications very well. Adoption, I think, is likely to be faster than JDK 17 because of virtual threads. I think people are quite excited about that. Anyone on JDK 11 who's going to migrate is probably going to skip JDK 17 and move directly to JDK 21 because there isn't really any big changes. Once you get past JDK 9, the migration path is very straightforward. Yeah, and try it on our Zulu builds of OpenJDK. So with that, that is the end of the presentation. Let's see if we have any questions. I do seem to be a couple of them. Right, so questions. I tried using JDK 21 in RHEL 8.6. I got socket connection reset in response to a post request. I gotta admit, I have no idea. I'd have to have a look at the code that you've been using. So I think that's one of those things. I'd try running it on a different operating system first, see whether it's related to that. But yeah, I've got absolutely no idea about that without looking at the code, I'm afraid. Second question, would virtual threads require higher CPU performance or more CPUs? Because if a platform thread is blocked and waiting on I/O, at least CPU is being used for other tasks. Yeah, you see, that's one of those interesting questions because it doesn't require higher CPU performance because the level of performance is going to be the same. So yes, ideally you're always going to want high level of CPU performance, but it is critical to that. The thing that you need to be careful about that, and I talked about that briefly, is when you're creating your when you're looking at switching to using virtual threads, you need to make sure that you're not going to spend a lot of time hogging the CPU. You need to say, well, okay, let the system, if it's doing I/O, then the thread can be reused by something else that does have work to do. So yeah, so because you see, if it is blocked on I/O, then that's good, unless you're in a synchronized block or method. So if you do block on I/O, that's good because it does free up the virtual thread to be used by other threads while it's waiting for that I/O to complete. Right. Okay. Yeah. So somebody's come back with that question about the socket exception. You tried Windows and it worked. Yeah, I would say that sounds to me like it's a bug If that's on the general GA version of JDK 21, I would actually log a bug against that because it sounds like something's not working in the way you expect it to. Another question here, would virtual threads behave differently with and without hyperthreading? When you mentioned OS thread there in the slide, did you mean CPU thread? Yeah, so hyperthreading from the JVM's point of view, hyperthreading is invisible. So the JVM is using operating system threads, and operating system threads are a layer of abstraction between the operating system thread model and whether it's using the hyperthreads or the threads in terms of the actual cores on the CPUs. So from a JVM point of view, it won't make any difference. And therefore, from a virtual thread point of view, it won't make any difference. Okay, so I don't see any other questions. And so what I'll say is, again, we have recorded this session. And so what we'll do is send out a link to this. So if you do want to review it again, or if you want to share it with other people, then you can do so. And with, hang on, one more question here. So the RX Java and Flux and Mono are going to be useless? No. Yeah. So what I would not recommend is if you are using RX Java already and you've got or Flux and Mono, then keep using them, because don't rewrite your code just to do something with virtual threads, because RX Java provides similar kind of functionality. I would leave it alone if it's working. It's only if you're migrating other kind of code to that. Okay, so with that, I will say thank you very much, and we will end the webinar.